Okay, so least squares problem, you've got some data, whatever the data means. And you want to fit a straight line to the data. Now it works whether you have a straight line or any degree polynomial, okay? But we're going to go with a straight line. It's easy enough to adapt the process to higher order polynomials at least. So first of all, to understand what we're trying to do is we want to maybe graph y versus x. So x goes out to 5. We'll divide our y-axis up so we have some convenient numbers, okay? So on the x we have 2, 1, 3, 4. And when x is 2, y is 7, so that gives us a point right about here. When x is 3, y is 11. That brings us up to about here. When x is 4, y is only 12, so not that much higher than 11. Okay? And when x is 5, y is like 19. So we've got this data that seems to be climbing. And it seems that maybe we can draw a straight line that fits this data pretty well. Okay? That's not a real good line. I should have tilted it more like this, but we get the idea. Okay? And this line let's see, go from 1 to, I'll say 17, rise of 16, run of 5. Okay? And that's not bad, but it's not the best you could possibly do. Now what you're ultimately trying to do, incidentally, is minimize the sum of the squares of the distances of the points above or below the line. Okay? And this is way too far, because squares, the bigger your discrepancy is, the bigger your square is going to be relative to everything else. Okay? So, this is not great. I can improve it. And if you learn to look at it, you can do a pretty good job. So I would say the best fit line is probably more like 3.4x minus 1 or something like that. Okay? I'm just eyeballing it. So this isn't bad, but it's clearly not the best. How do we get the best? Okay? Well, we want to find A and B, and I'm not sure I've got, I want to look at your book's notation again, but such that okay, is as close to the data as possible in the sense of minimizing the total of the squared discrepancies. And I'm not going to go to a complete definition of that because I don't really need it, to just give you a sketch of how we do this, okay? Well, then, and I do want to stop for a second and look at the notation in your book. So basically we have a matrix equation AB equals C, where C is a vector in a two-dimensional subspace. Okay? And V is a vector of your y values. Okay? So I want to get the notation straight before I show you a couple of details.